The universe is a vast, mysterious place filled with wonders that defy our understanding. Look up at the night sky, and you're staring into an endless cosmic puzzle, one where even the darkest corners hide secrets that challenge everything we think we know. Among these enigmas, few are as baffling or as thrilling as primordial black holes. These aren't your typical black holes born from collapsing stars. No, these are relics from the very dawn of time, theoretical anomalies that might have formed in the first moments after the Big Bang. And if they exist, they could rewrite the rules of astrophysics as we know them. Imagine something so dense, so powerful, that it could fit in the palm of your hand yet contain the mass of a mountain. These tiny cosmic titans, if they're out there, could be lurking unseen in our galaxy, hidden in plain sight. Some scientists think they might even be the elusive dark matter we've been searching for. Others believe they could be the seeds of supermassive black holes, the monsters that lurk at the centers of galaxies. And then there are the wilder ideas, like the possibility that they're gateways to other dimensions or even time machines in disguise. The theories are as mind-bending as they are numerous. Today, we're diving deep into 30 of the most fascinating ideas about primordial black holes, from their role in shaping the early universe to the eerie ways they might still be influencing it today. We'll explore the science, the speculation, and the sheer wonder of these cosmic oddities. Whether you're a seasoned space enthusiast or just curious about the universe's biggest mysteries, there's something here to blow your mind. So buckle up, this journey is going to take us to the edges of reality and back. One of the most compelling theories about primordial black holes suggests they might be the missing piece to one of cosmology's greatest mysteries, dark matter. For decades, scientists have known that something invisible makes up most of the universe's mass, bending light and holding galaxies together. Yet traditional particles like WIMP or actions have remained frustratingly elusive. But what if the answer isn't some exotic particle at all? What if it's these ancient, ultra-dense remnants from the Big Bang itself? Here's how it could work. Unlike black holes formed from dying stars, primordial black holes could have popped into existence in the chaotic first moments of the universe, when extreme density fluctuations allowed matter to collapse directly into tiny, high-mass objects. If enough of them formed, they might now be drifting unseen through galaxies, including our own. They wouldn't emit light, and if they're small enough, say, the size of an atom or a tennis ball, they'd be nearly impossible to detect with current telescopes. But there's a catch. For primordial black holes to account for all dark matter, they'd need to be distributed in just the right way. Too many, and their gravitational effects would tear apart star clusters or distort the cosmic microwave background in ways we don't observe. Too few, and they couldn't explain the missing mass. Some researchers think a specific mass range, around that of a small asteroid, might strike the perfect balance, plentiful enough to add up, but subtle enough to stay hidden. This theory isn't without rivals. Other dark matter candidates, like hypothetical weakly interacting particles, still have strong support. But primordial black holes offer something unique, a solution that doesn't require new physics, just the natural consequences of the early universe's wild conditions. And if they're real, they could be everywhere, passing through you right now without a trace. That's the eerie beauty of this idea. The answer to one of science's biggest questions might have been hiding in plain sight all along, written in gravity's invisible ink. What if the universe itself, in its earliest violent moments, forged primordial black holes, not from collapsing stars, but from the raw energy of creation itself? This leads us to our next theory, where the seeds of these mysterious objects may have been planted during cosmic inflation, that mind-boggling fraction of a second when the infant universe expanded faster than the speed of light. Inflation wasn't smooth. Quantum fluctuations, tiny, random ripples in spacetime bubbled up everywhere, most smoothed out, but some grew wildly dense, like knots in a stretching rubber sheet. Under the right conditions, these knots could have collapsed under their own gravity, forming microscopic black holes almost instantly. Think of it like boiling water. Random bubbles form and pop, but in the universe's case, some bubbles became permanent cosmic scars. Here's where it gets wild. For a black hole to form this way, the density of those fluctuations had to cross an astronomical threshold. We're talking about regions hundreds of times denser than the surrounding space, cramming enough mass into a speck smaller than an atom to trigger gravitational collapse. That sounds extreme, but inflation's environment was anything but ordinary. Energy densities were so high that the laws of physics as we know them might have temporarily bent, making such extreme events possible. What's fascinating is that inflation could have churned out black holes across a vast spectrum of sizes, from ones lighter than a paperclip to monsters rivaling planets. The smaller ones might have evaporated almost immediately due to Hawking radiation, but the larger survivors could still be out there, drifting through the cosmos undetected. Some models even suggest inflation's fingerprints might be hidden in the distribution of these black holes today, like echoes of the universe's first breath. Critics argue that inflation's parameters would need fine-tuning to produce the right number of black holes without over-cluttering the early universe. Too many and they'd disrupt galaxy formation, too few and they'd be irrelevant. Yet if the math holds, this theory elegantly ties two cosmic mysteries together: inflation's quantum origins and the potential existence of primordial black holes, offering a glimpse into how the universe's most violent beginnings might still shape its hidden fabric today. At the heart of nearly every large galaxy, including our own Milky Way, lurks a supermassive black hole, a gravitational behemoth millions or even billions of times heavier than our Sun. How these cosmic giants grew so enormous so quickly remains one of astrophysics' most perplexing puzzles. The universe simply didn't seem to have enough time for them to form from ordinary stellar collapses. But what if they didn't start from scratch? What if they were born from something far smaller yet unimaginably ancient primordial black holes? This theory proposes that the titans at galactic centers grew like snowballs rolling downhill, starting as tiny primordial black holes formed in the universe's infancy. Picture this: in the chaotic aftermath of the Big Bang, countless microscopic black holes peppered the cosmos. Over billions of years, their immense gravity would have pulled in surrounding gas and dust, merging with other black holes along the way. Each collision and meal added mass, gradually transforming these specks of primordial darkness into the monsters we observe today. The math behind this idea is surprisingly elegant. Primordial black holes could have served as seeds, giving supermassive black holes a colossal head start. Without them, conventional models struggle to explain how these giants accumulated enough material so rapidly. But with even a small population of primordial seeds scattered across the early universe, gravity would have done the rest, funneling matter into their insatiable grip. Simulations show that under the right conditions, a black hole the mass of a small star could balloon into a supermassive beast within a cosmic blink, relatively speaking. Yet proving this theory is anything but straightforward. For one, we'd need to find evidence of intermediate-sized black holes, missing links between primordial specks and galactic titans. Some candidates have been spotted, like the mysterious objects lurking in globular clusters, but their origins remain debated. Another challenge lies in the chaotic environments of early galaxies, where competing forces like radiation pressure and supernova could have disrupted the steady diet of gas needed for growth. And if primordial black holes were too numerous, their mergers might have left detectable ripples in space-time, gravitational waves we haven't yet observed. Still, the idea holds a haunting appeal. It suggests that the largest structures in today's universe were shaped by the smallest quirks of the ancient past. If true, every supermassive black hole could carry a hidden lineage, tracing back to the violent first moments of existence. The next generation of telescopes, like the James Webb Space Telescope and future gravitational wave detectors, might finally sniff out these cosmic breadcrumbs, revealing whether our galaxy's heart grew from a seed sown at the dawn of time. Stephen Hawking gave us one of the most startling revelations about black holes. They might not be eternal. In the 1970s, he proposed that black holes could actually evaporate over cosmic timescales, slowly leaking energy into space through a phenomenon now known as Hawking radiation. This idea turns our understanding of these cosmic vacuum cleaners on its head, especially when applied to primordial black holes. If they formed in the early universe, could some have already disappeared? And why might others still linger in the darkness today? Hawking radiation arises from quantum mechanics playing tricks at the very edge of a black hole's event horizon. According to quantum theory, empty space isn't truly empty. It's a bubbling sea of virtual particles popping in and out of existence. Normally, these particle pairs annihilate each other instantly. But near a black hole's boundary, one particle might fall in while the other escapes, stealing a tiny bit of the black hole's mass in the process. Over time, this slow leak causes the black hole to shrink and eventually vanish in a final burst of energy. Now, here's where things get interesting for primordial black holes. Their lifespans depend critically on their initial mass. A black hole with the mass of our Sun would take an unimaginable 10 to the power of 67 years to evaporate, far longer than the current age of the universe. But a much smaller one, say, the mass of a mountain crammed into the size of a proton, could disappear in just a few billion years. That means some of the tiniest primordial black holes, if they ever existed, might have already burst apart like cosmic fireworks, leaving behind faint traces of gamma rays or other radiation. Why then do scientists think some primordial black holes might still be around? It all comes down to size. Those with masses above a certain threshold, roughly equivalent to a small asteroid, would still be in the slow, steady phase of evaporation, their lifespan stretching trillions of years into the future. These survivors would be too faint to emit noticeable radiation today, making them nearly invisible to our telescopes, yet their gravitational influence could still betray their presence. This creates a tantalizing possibility. If we could detect the faint glow of an evaporating primordial black hole or spot the gravitational lensing effects of one drifting silently through space, it would confirm not only Hawking's theory but also their existence. Some astronomers are actively searching for these signals, scanning the sky for unexpected bursts of gamma rays or distortions in starlight that might reveal a hidden population of ancient black holes. Critics point out that Hawking radiation itself has never been directly observed, making the entire premise speculative. Others argue that even if primordial black holes exist, their evaporation might leave no detectable trace. Yet the stakes are high. If we found one, it wouldn't just validate Hawking's work. It would open a window into the universe's earliest moments, offering clues about the conditions that birthed these enigmatic objects. The beauty of this theory lies in its duality. Hawking radiation suggests that even the darkest corners of the cosmos aren't permanent. Some primordial black holes may have already faded into nothingness, while others continue their slow dance toward oblivion. Their lifespans act as cosmic clocks, ticking away since the dawn of time, silent witnesses to the universe's grand, evolving story. The early universe wasn't the smooth, uniform canvas we might imagine. Instead, it was a turbulent sea of density variations, pockets of space slightly denser or thinner than their surroundings. These fluctuations might seem insignificant, but they held the blueprint for everything that followed: galaxies, stars, and even the cosmic web itself. And here's where primordial black holes enter the picture. What if these ancient relics weren't just cosmic accidents, but the direct result of those early density extremes? Take a closer look at the cosmic microwave background, the afterglow of the Big Bang. This faint radiation, visible across the entire sky, carries faint imprints of those primordial density variations. Most of these fluctuations are subtle, but some regions stand out anomalies that don't quite fit our models. One possible explanation: primordial black holes forming in the densest patches, their immense gravity warping the surrounding space and leaving behind telltale distortions. Picture the universe in its first fractions of a second, a seething maelstrom of energy and matter. In regions where the density spiked dramatically, gravity could have overpowered the outward pressure of expansion, causing matter to collapse directly into black holes. These wouldn't be the orderly black holes born from dying stars, but chaotic remnants of the universe's raw infancy. If enough of them formed, they could have seeded the uneven distribution of matter we see today, acting as gravitational anchors that drew in gas and dust to build the first structures. The cosmic microwave background offers tantalizing clues. Some of its temperature variations, slightly hotter or colder spots, don't align perfectly with standard cosmology. Could these be the fingerprints of primordial black holes subtly bending the path of light as it traveled through the early universe? Simulations suggest that even a sparse population of these objects could create detectable ripples in the radiation, like stones disturbing the surface of a pond. Critics argue that other phenomena, like exotic energy fields or quantum effects, could explain these anomalies just as well. But primordial black holes have a unique advantage: they don't require new physics beyond what we already suspect existed in the early universe. They're a natural consequence of gravity doing what gravity does in extreme conditions. And if they're responsible for those early density variations, they wouldn't just be cosmic oddities. They'd be the architects of the universe's large-scale structure, hidden hands that shape the cosmos from the shadows. The implications stretch even further. If primordial black holes seeded the first galaxies, they might have determined where and how stars formed, influencing the universe's evolution in ways we're only beginning to grasp. Future telescopes, like the upcoming LIGHT-BIRD mission, could hunt for their faint signatures in the cosmic microwave background with unprecedented precision. A confirmed detection wouldn't just solve one mystery, it would rewrite our understanding of how the universe grew from a fiery beginning into the intricate tapestry we see today. The beauty of this theory lies in its simplicity. The early universe was a place of extremes, and primordial black holes could be the natural outcome of its wildest moments. They might not just be relics of the past, but the very reason the cosmos looks the way it does: silent sculptors of the universe's grand design. Gravitational waves, ripples in the fabric of space-time, have revolutionized our understanding of the cosmos since their first detection in 2015. But what if some of these elusive signals aren't coming from the mergers of star-born black holes we've observed so far? What if they're the echoes of primordial black holes colliding in the darkness, remnants of the universe's birth throes? When two primordial black holes spiral toward each other, their immense gravity warps space-time so violently that the shockwaves can travel across billions of light-years. Unlike black holes formed from stars, which typically pair up in binary systems, primordial black holes would merge more randomly, scattered by the chaos of the early universe. This could produce gravitational waves with distinctive signatures, slightly different frequencies, durations, or even patterns than those from stellar black hole mergers. LIGO, the Laser Interferometer Gravitational Wave Observatory, has already spotted dozens of collisions, but none definitively point to primordial origins. That's partly because the signals overlap with what we'd expect from conventional black holes. But here's the twist: primordial black holes could span a much wider mass range, from lighter than a feather to heavier than a star. If a merger involved an unusually light or heavy black hole, or an asymmetric pair, it might stand out as a potential primordial candidate. Future detectors could be game changers. Upgraded versions of LIGO, like the Cosmic Explorer, or space-based observatories like LISA, will listen for lower frequency waves, potentially catching the mergers of supermassive primordial black holes. Even more intriguing are the tiny, high-frequency waves from minuscule black holes evaporating via Hawking radiation signals no current detector can pick up, but which might be within reach of next-generation technology. Some theorists argue that if primordial black holes are abundant, their mergers should have left a stochastic background, a faint, omnipresent hum of gravitational waves from countless collisions over cosmic history. This noise hasn't been detected yet, but as instruments grow more sensitive, we might soon hear the universe's oldest whispers. Critics caution that without a smoking gun signal, like a merger involving a black hole far outside the expected mass range for stellar collapses, the primordial origin remains speculative. But if even one event defies conventional explanations, it could crack open a window to the universe's first moments. Imagine, every gravitational wave detection might not just be a snapshot of black holes colliding, but a relic of the cosmos itself being stitched together. Quasars are some of the most luminous objects in the universe, beaming out enough light to outshine entire galaxies from billions of light-years away. At their cores lie supermassive black holes, greedily devouring surrounding matter and converting it into blinding energy. But here's the puzzle. Many quasars existed when the universe was less than 1 billion years old, raising an obvious question. How did their black holes grow so massive so fast? One provocative theory suggests primordial black holes might have jump-started the process, acting as ready-made fuel for these cosmic furnaces from the very beginning. Imagine a primordial black hole drifting through the dense gas clouds of the early universe. Even a relatively small one, say, the mass of a star, would exert a tremendous gravitational pull, sucking in gas at a ferocious rate. As material spirals inward, friction heats it to millions of degrees, forming a glowing accretion disk that unleashes torrents of radiation. Normally, black holes forming from stellar collapses take time to bulk up. But a primordial black hole wouldn't need that time. It would already be there, a pre-existing gravitational trap in the perfect position to feast on the universe's primordial buffet. This scenario gets even more compelling when you consider the sheer efficiency of these systems. Quasars convert matter into energy with mind-bending efficiency, far outpacing nuclear fusion. A typical star turns less than 1% of its mass into energy, while a quasar's accretion disk can hit 10% or more. If primordial black holes seeded these monsters early on, they'd have had a head start, growing exponentially as they swallowed gas and dust. Simulations show that a single primordial black hole in a gas-rich environment could balloon into a quasar's engine within a few 100 million years, fast enough to explain the dazzling quasars we spot in the infant cosmos. But there's a catch. For this to work, primordial black holes would need to cluster in just the right places, dense regions where gas was plentiful. Too scattered and they'd starve, too concentrated and their gravity might disrupt galaxy formation. Some models suggest that quantum fluctuations in the early universe could have naturally created these dense pockets, sprinkling them with black hole seeds. Others argue that primordial black holes might have migrated toward gas-rich centers over time, drawn by the same gravity that fed their growth, the smoking gun. Look for quasars in the very early universe, ones that existed when conventional black holes wouldn't have had time to form. The James Webb Space Telescope has already spotted several candidates, their light dating back to when the universe was barely 700 million years old. If future observations reveal that these quasars are more common than expected, or that their black holes are oddly massive for their age, it could point to a primordial origin. Critics counter that even without primordial black holes, gas dynamics in the early universe might have allowed rapid growth through alternative means, like super-Eddington accretion, where black holes consume material faster than theoretical limits predict. But the elegance of the primordial seed theory lies in its simplicity. It doesn't require exotic physics, just the right conditions for ancient black holes to tap into the universe's raw energy reserves. Whether or not this theory holds, it underscores a thrilling possibility. The brightest beacons in the cosmos might owe their existence to the darkest relics of creation. Every quasar's glare could be the afterlife of a primordial black hole's feast, a cosmic whisper from a time when the universe was just learning how to shine. Dark matter doesn't just float aimlessly through space, it clumps together in vast, invisible structures called halos, whose gravity holds galaxies together like cosmic scaffolding. But what if these halos aren't made of exotic particles at all? What if they're actually dense, swirling clusters of primordial black holes, their combined gravity mimicking the effects we've attributed to dark matter for decades? This theory flips the script on conventional dark matter models. Instead of relying on hypothetical particles like WIMP or actions, it suggests that primordial black holes could have naturally grouped together in the early universe, drawn into tight knots by their own gravity. Picture a swarm of bees orbiting a hive, except each bee is a black hole with the mass of a small moon, and the hive is the center of a galaxy. Together, their gravitational pull would be indistinguishable from the smooth, diffuse halos predicted by particle-based theories. There's compelling math behind this idea. Simulations show that if primordial black holes make up even a fraction of dark matter, their interactions would cause them to cluster in ways that mirror the distribution we observe. They'd tend to gather toward galactic centers just like particle halos, while also flinging some outliers into diffuse, far-reaching orbits, the key difference. Particle halos are thought to be perfectly smooth, while black hole clusters would have subtle density spikes, tiny gravitational hotspots where individual black holes pass close to one another. Detecting these spikes is the real challenge. Current telescopes can't resolve such fine details in distant halos, but there are indirect ways to hunt for them. For example, if a primordial black hole cluster drifted between Earth and a distant star, the star's light would briefly flicker as multiple black holes magnified and distorted it, a phenomenon called gravitational microlensing. Surveys like the OGLE project have spotted rare lensing events, but so far, none definitively point to clustered black holes. Critics argue that if primordial black holes were this abundant, their mergers would have flooded the universe with detectable gravitational waves, a signal we haven't yet observed. Others counter that black holes in clusters might avoid collisions, slingshotting past each other instead of merging. The debate hinges on a delicate balance: too many close encounters and the waves would be obvious, too few and the clusters stay silent. What makes this theory so fascinating is its audacity. It doesn't just tweak the dark matter puzzle, it rewrites the ingredients entirely. If correct, our galaxy's halo might not be a cloud of invisible particles but a shadowy archipelago of ancient black holes, each a fossil from the universe's first second. Future telescopes could settle the debate by mapping halos in unprecedented detail, searching for the gravitational fingerprints that would betray a hidden swarm. Until then, the idea lingers, a reminder that the universe's darkest secrets might be stranger than we've dared to imagine. The universe holds a peculiar accounting problem. Billions of tons of ordinary matter seem to be missing. Scientists call this the missing baryon problem, and it's one of cosmology's nagging inconsistencies. We know how much matter should exist based on the Big Bang's nuclear reactions, but when we tally up all the visible stars, gas and dust, the numbers don't add up. Could primordial black holes be the elusive culprit, hiding this missing matter in their inescapable grasps? Let's rewind to the universe's first few minutes, when protons and neutrons, the building blocks of ordinary matter, formed in a process called Big Bang nucleosynthesis. The math here is precise. The density of baryonic matter affects how elements like hydrogen and helium were forged. Observations of ancient gas clouds and the cosmic microwave background align beautifully with these predictions, except when we compare them to the matter we actually see today. A significant fraction, perhaps up to half, has vanished without a trace. Primordial black holes present an elegant solution. If they formed before nucleosynthesis, they'd have locked away baryons, protons, and neutrons before those particles could contribute to the visible universe. Unlike dark matter, which is thought to be entirely separate from ordinary matter, these black holes would essentially be hidden baryons, their mass still part of the cosmic budget but invisible to telescopes. But there's a catch. For this theory to hold, primordial black holes must avoid tripping over other cosmic clues. Take cosmic rays, for example. If too many baryons were swallowed by black holes, the high-energy particles streaking through space would show unusual gaps in their composition, patterns we haven't observed. Similarly, the delicate balance of light elements forged in the Big Bang narrows the window for when and how many black holes could have formed without disrupting the recipe. Here's where things get interesting. Some models suggest that only a specific mass range of primordial black holes, those between the weight of a small asteroid and a dwarf planet, could reconcile these constraints. Too large, and their formation would have left scars in the cosmic microwave background. Too small, and they'd have evaporated by now, releasing their trapped baryons back into the wild. But if they're just the right size, they could lurk undetected, their gravitational presence the only hint of the missing matter they've hoarded. Critics argue that alternative explanations, like diffuse gas hiding in intergalactic filaments, might account for the discrepancy without invoking black holes. Others point out that even if primordial black holes exist, they'd need to be finely tuned to avoid contradicting other observations, like the distribution of gamma rays or the behavior of neutron stars. Yet the idea persists partly because it doesn't require new physics, just a clever repurposing of gravity's oldest trick. The beauty of this theory lies in its duality. Primordial black holes could solve two puzzles at once, the dark matter mystery and the missing baryon problem. Or they might be a red herring, a tantalizing dead end in the quest to balance the universe's books. Either way, the search forces us to confront a humbling truth that the cosmos keeps its ledgers in ways we're only beginning to decipher. Future observations could tip the scales. Projects like the Vera Rubin Observatory might spot the subtle gravitational lensing effects of these hidden black holes, while gamma-ray telescopes could catch the faint afterglow of their long-ago evaporations. Until then, the missing baryons remain a cosmic IOU, a reminder that even the ordinary matter we think we understand might be hiding in the darkest corners of the universe's ledger. Cosmic rays streak across the universe at energies so extreme, they make particle accelerators like the Large Hadron Collider look like toys. These subatomic bullets, mostly protons and atomic nuclei, carry millions of times more energy than anything we can produce on Earth. But their origins remain one of astrophysics' thorniest puzzles. Some of these rays are so powerful, physicists struggle to explain what natural process could possibly launch them. Enter primordial black holes, whose extreme environments might be cosmic ray factories operating in the shadows. Picture a primordial black hole drifting through interstellar space, its immense gravity pulling in nearby gas and dust. As this material spirals inward, it doesn't just vanish. It forms a superheated plasma, a swirling soup of charged particles moving at nearly the speed of light. In this chaotic maelstrom, magnetic fields twist and snap like rubber bands, accelerating particles to staggering energies. Under the right conditions, these particles could break free, catapulted into space as ultra-high-energy cosmic rays. But there's another, even wilder possibility. Remember Hawking radiation. As tiny primordial black holes evaporate, their final moments might unleash a cataclysmic burst of energy. Theoretical models suggest that the last stages of evaporation could resemble a miniature Big Bang, releasing a concentrated spray of high-energy particles. If this happens near enough to Earth, these dying black holes might be the source of the mysterious cosmic rays we've detected, particles with energies so high they shouldn't exist under conventional physics. The evidence is circumstantial but tantalizing. Some ultra-high-energy cosmic rays arrive from seemingly empty regions of space, with no obvious astrophysical sources like supernova or active galaxies nearby. Others exhibit strange clustering patterns, as if multiple rays originated from the same point, behavior that could align with localized bursts from evaporating primordial black holes. Critics point out that known astrophysical phenomena like shock waves from galaxy collisions could also explain these rays, and without direct detection of a primordial black hole's evaporation burst, the theory remains speculative. But upcoming observatories like the Cherenkov Telescope Array may soon spot the telltale gamma-ray flashes that would confirm these tiny cosmic detonations. What's fascinating is how elegantly this theory ties together two cosmic enigmas. Primordial black holes, if they exist, wouldn't just lurk unseen. They'd actively sculpt the universe's most energetic phenomena. Every ultra-high-energy cosmic ray could be a message from one of these ancient objects, a final shout across the cosmos before fading into nothingness. Whether they're the source or not, the mere possibility stretches our imagination, proving once again that the darkest objects might hold the keys to the universe's brightest mysteries. Black holes aren't just cosmic vacuum cleaners, they're also laboratories for some of the strangest physics imaginable. And when it comes to primordial black holes, their tiny sizes might unlock phenomena we've never seen before. Picture a black hole so small, its event horizon is narrower than an atom. At that scale, quantum mechanics and gravity collide in ways that could twist the rules of reality, creating bizarre atmospheres of swirling virtual particles and warping spacetime into knots. Imagine hovering just outside the event horizon of one of these microscopic monsters. According to quantum theory, empty space isn't empty at all. It's a frothing sea of virtual particles popping in and out of existence. Normally, these particle pairs annihilate each other instantly, but near a black hole's edge, the gravitational pull is so extreme that one particle gets sucked in while the other escapes, becoming real energy. This is Hawking radiation in action, but for a primordial black hole, the process could get even weirder. The smaller the black hole, the more intense its Hawking radiation. A speck-sized primordial black hole might be surrounded by a dense, shimmering haze of virtual particles, like a storm of quantum fireworks constantly sparking at its surface. Some theorists suggest these atmospheres could exhibit exotic behaviors, particles with unnatural energies, fleeting distortions in the fabric of space-time, or even hints of extra dimensions predicted by string theory. Under these extreme conditions, the usual boundaries between quantum mechanics and general relativity might blur, offering clues to a unified theory of physics. String theory adds another layer of strangeness. If extra dimensions exist, a tiny black hole could probe them directly, its gravity leaking into higher dimensional space. This leakage might alter how Hawking radiation works, producing unique signatures in the particle haze. Some models even predict that primordial black holes could briefly tunnel into these extra dimensions, creating temporary quantum bridges to other realms. Far-fetched maybe, but if we ever detected a black hole emitting particles with impossible energies or patterns, it could be smoking gun evidence for physics beyond our current understanding. Then there's the wild card, quantum entanglement. When virtual particles split at the event horizon, their fates become intertwined across unimaginable distances. A primordial black hole's atmosphere might be threaded with these quantum connections, essentially weaving a web of entanglement that stretches across the universe. If we could study such a system, it might reveal how black holes process information, a puzzle at the heart of the infamous black hole information paradox. Of course, observing these effects directly is a monumental challenge. The atmospheres would be faint, fleeting, and buried in quantum noise. But next-generation detectors like ultra-sensitive particle colliders or space-based quantum sensors might one day catch whispers of these exotic phenomena. Even the Large Hadron Collider has briefly toyed with the idea of creating microscopic black holes, though none have appeared yet. critics argue that without experimental proof, these ideas remain speculative daydreams. But that's the thrill of primordial black holes. They're not just cosmic relics. They're keys to unlocking realms of physics we can barely imagine. Whether they're shrouded in quantum storms or bridging hidden dimensions, these tiny titans could hold the answers to questions we haven't even thought to ask yet. And if we ever find one, it won't just rewrite astrophysics textbooks, it could redefine reality itself. The idea of extra dimensions sounds like pure science fiction until you realize it might be the key to unlocking the true nature of primordial black holes. String theory, the leading candidate for a theory of everything, suggests our universe could have more than the three spatial dimensions we experience daily. These hidden dimensions, curled up at scales far smaller than an atom, might have played a crucial role in the formation and behavior of primordial black holes, warping their physics in ways that defy conventional understanding. Take evaporation rates, for example. In our familiar four-dimensional spacetime, Hawking radiation causes black holes to shrink and eventually vanish. But add extra dimensions into the mix and the math changes dramatically. Gravity in higher dimensional theories isn't confined to our visible universe, it can leak into these hidden realms. For a primordial black hole, this leakage would intensify its gravitational pull at very small scales, accelerating its evaporation. A black hole that might take trillions of years to disappear in four dimensions could evaporate in mere millennia, or even centuries if it's tapping into extra-dimensional gravity. This opens a tantalizing detection window. If primordial black holes are evaporating faster due to extra dimensions, their final moments could produce bursts of energy far brighter than expected. Instead of fading quietly, they might go out with a bang, releasing gamma rays, neutrinos, or even exotic particles unique to higher dimensional physics. Telescopes designed to catch these fleeting signals, like gamma-ray observatories or neutrino detectors, might stumble upon evidence not just of primordial black holes, but of the extra dimensions themselves. But there's a flip side. Extra dimensions could also make forming primordial black holes easier in the first place. In the early universe, when energies were unimaginably high, these hidden dimensions might have unfurled, lowering the density threshold needed for gravitational collapse. Regions of space that would have been too diffused to form black holes in four dimensions could have collapsed instantly in 5 or 6, sprinkling the cosmos with countless microscopic black holes. Some models even suggest this could explain why we haven't found them yet. They evaporated too quickly, leaving behind only faint higher dimensional echoes. Critics argue that without direct proof of extra dimensions, this theory remains speculative, but tantalizing hints exist. The Large Hadron Collider has hunted for microscopic black holes that could form if extra dimensions are real, though none have appeared yet. Meanwhile, anomalies in high-energy cosmic rays particles with energies that seem to defy known physics might be indirect traces of black holes dissolving into higher dimensional space. The beauty of this idea is how it ties together two of physics' biggest mysteries. Primordial black holes aren't just cosmic relics, they could be probes into the hidden architecture of reality itself. Finding one might not just rewrite the history of the universe, it could reveal that the cosmos is far vaster and stranger than we ever imagined. What if primordial black holes aren't just cosmic relics, but time capsules locking away secrets from before the Big Bang itself? This radical theory suggests these ancient objects could preserve information from a universe that existed before ours, a possibility that twists our understanding of time, causality, and the very nature of reality. Consider the firewall paradox, one of modern physics' most puzzling thought experiments. When matter falls into a black hole, quantum mechanics insists that the information it carries can't be destroyed, yet general relativity claims it's irretrievably lost behind the event horizon. Some theorists argue this contradiction implies an inferno of high-energy particles, a firewall burning at the boundary. but primordial black holes could rewrite this paradox entirely. If they formed in the pre-Big Bang era, their event horizons might operate under different quantum rules, acting as cosmic vaults that encode information in ways we can't yet fathom. Imagine these black holes as cosmic amber, trapping quantum states from an earlier epoch like insects frozen in resin. The extreme conditions of their formation, where the very fabric of space-time was pliable, might have allowed unusual information-preserving mechanisms. One compelling idea involves quantum entanglement across time, where particles inside the black hole remain eerily linked to states that existed before the singularity of the Big Bang. This wouldn't just preserve information, it could create a bridge between universes, a thread connecting our cosmos to whatever came before. The implications are staggering. If we could somehow decode the Hawking radiation from an evaporating primordial black hole, we might find imprints of pre-Big Bang physics, mathematical patterns, or quantum fluctuations that don't match our universe's initial conditions. Some models even suggest these black holes could contain baby universes, in their cores tiny space-time bubbles where the laws of physics diverge from our own. Critics counter that without experimental evidence, this remains speculative poetry. Yet the math hints at tantalizing possibilities. Future gravitational wave detectors might catch subtle distortions in space-time around ancient black holes, revealing anomalies that point to their extraordinary origins. Until then, these mysterious objects stand as potential keys not just to our universe's birth, but to realities we've yet to dream of. Galaxies didn't just appear fully formed in the early universe, they grew piece by piece from tiny seeds of gravity. But what planted those seeds? The prevailing theory points to cold dark matter, an invisible scaffolding that slowly pulled gas and dust into the galaxies we see today. Yet there's another contender lurking in the shadows of primordial black holes. These ancient relics, if they existed in just the right numbers, could have jump-started galaxy formation long before ordinary matter had time to clump together on its own. Picture the universe a few 100 million years after the Big Bang, a vast, mostly empty expanse dotted with faint wisps of hydrogen gas. Without something to concentrate that gas, the first stars and galaxies might have taken eons to emerge. Cold dark matter solves this problem by providing a gravitational anchor. Its invisible particles clump together first, creating wells of gravity that ordinary matter then cascades into. But primordial black holes offer a twist on this story. Instead of relying on diffuse particles, they'd be concentrated points of immense gravity, like boulders dropped into a pond, creating ripples that gas couldn't ignore. Simulations tell a fascinating tale. Run a model with cold dark matter alone, and galaxies form gradually, their structures smooth and predictable. But introduce primordial black holes into the mix and things get interesting. These microscopic gravity wells would act like cosmic catalysts, accelerating the collapse of gas clouds into stars and galaxies far earlier than expected. Some calculations suggest that even a sparse population of primordial black holes could have shaved hundreds of millions of years off the timeline for galaxy formation, explaining why we see fully mature galaxies in the very young universe. The differences don't stop there. Cold dark matter spreads its gravitational influence evenly, leading to galaxies with fluffy, extended halos. Primordial black holes, on the other hand, would leave a more jagged imprint, pockets of intense gravity that could produce galaxies with unusual features, denser cores, sharper edges, or even bizarre, lopsided shapes. Telescopes like the James Webb Space Telescope are now spotting galaxies from this cosmic dawn, and some of them defy expectations. Could these oddballs be the fingerprints of primordial black holes at work? Critics raise valid concerns. If primordial black holes were too numerous, their gravity would have torn apart delicate structures like dwarf galaxies or distorted the cosmic microwave background in ways we don't observe. Yet supporters counter that a carefully balanced population, just enough to seed galaxies but not so many to wreak havoc, could fit the data beautifully. It's a cosmic Goldilocks problem. Not too many, not too few, but just right. The stakes couldn't be higher. If primordial black holes played even a minor role in galaxy formation, it would force us to rethink how the cosmos built its grandest structures. Instead of a slow, steady process guided by invisible particles, the early universe might have been a place of sudden, dramatic collapses, where tiny black holes acted as gravitational sparks, igniting the fires of creation far sooner than we ever imagined. The next generation of telescopes, peering deeper into space and further back in time, may finally reveal which theory holds the key to the universe's first light. The Fermi Paradox asks a haunting question. If the universe is teeming with potential for life, why haven't we heard from anyone else? Countless explanations have been proposed, from self-destructive civilizations to elusive alien behaviors. But what if the answer isn't about biology or sociology at all? What if the silent cosmos hides a far deadlier threat, one drifting unseen between the stars? Primordial black holes might be the universe's ultimate landmines, lurking in the darkness with the power to annihilate civilizations before they ever get the chance to call out into the void. Consider the numbers. Even if primordial black holes make up just a fraction of dark matter, the sheer scale of the galaxy means there could be billions of them scattered across the Milky Way. Most would pass harmlessly through the vast emptiness of space, but every so often one might wander too close to a star or a planet. The odds of a direct collision are vanishingly small, but over cosmic timescales, rare events become inevitable. A black hole, the mass of a mountain, smaller than an atom but packing unimaginable density, wouldn't just strike a planet like a bullet. It would pass straight through, unleashing tidal forces strong enough to rip continents apart, trigger volcanic Armageddon, or strip away an atmosphere in moments. The devastation would be swift, total, and utterly invisible until it was too late. Now imagine a thriving alien civilization, one that's mastered interstellar travel or built sprawling megastructures around its star. All it would take is one unseen primordial black hole, drifting through their system at a fraction of light speed, to turn their achievements to dust. The aftermath wouldn't leave debris or ruins, just silence. No radio signals, no Dyson spheres, no signs of a catastrophe we'd even recognize. Just another empty patch of space where life might have been, but never got the chance to flourish long enough for us to notice. Could this explain the eerie quiet of the cosmos? The math offers sobering clues. Even if only 1 in a million star systems ever suffers such a collision, multiply that across billions of years and trillions of stars, and it starts to paint a grim picture. Civilizations might bloom like fragile flowers in a minefield, their lifespans cut short not by war or folly, but by pure cosmic bad luck. Of course, skeptics have counter-arguments. If primordial black holes were this destructive, Earth should have faced extinction long ago. Yet here we are. Maybe we've just been lucky, or maybe the distribution of these objects leaves safe pockets where life can thrive. Others point out that advanced civilizations might detect gravitational anomalies and evacuate before impact, though predicting the path of something so small and dark would be nearly impossible. The chilling beauty of this theory is its simplicity. It doesn't require alien conspiracies or mysterious filters, just cold, random physics, a universe where the seeds of creation double as agents of oblivion. If true, the silence isn't a puzzle to solve. It's the sound of the cosmic dice rolling over and over, with life itself in the balance. A solar system is a delicate dance of gravity, planets circling stars in rhythms that have held steady for billions of years. But what happens when an invisible intruder crashes the party? Primordial black holes drifting unseen through the galaxy could be cosmic wrecking balls, their gravitational fists capable of knocking worlds off course or even dragging them into eternal darkness. Picture a primordial black hole no larger than a baseball, but weighing as much as Earth, streaking through our solar system at hundreds of kilometers per second. It wouldn't announce itself with a flash or a crash. Instead, its presence would ripple through space like a stone dropped in a pond, warping the paths of everything it passed. Planets wouldn't be knocked aside like billiard balls. Their orbits would stretch and wobble, subtly or dramatically altered depending on the black hole's mass and proximity. A close encounter might fling a planet into a wild, elliptical orbit, turning a temperate world into a frozen wasteland or a scorching hellscape, a direct hit. That's a one-way ticket to oblivion swallowed whole with barely a whisper. But here's where it gets stranger. Some models suggest that under the right conditions, a primordial black hole could be captured by a star or gas giant's gravity, trapped in a slow, eternal orbit. Imagine Jupiter harboring a secret lodger, a black hole nestled in its core, gradually devouring it from the inside out. Over millennia, the planet's atmosphere would spiral inward, vanishing without a trace as the black hole fed. Astronomers scanning the skies might spot an anomaly, a gas giant mysteriously losing mass or a star wobbling as if tugged by an unseen companion. These could be the fingerprints of a primordial black hole hiding in plain sight. The implications are staggering. If even a handful of these rogue black holes drift through our galaxy, they could explain some of astronomy's oddest misfits, planets with bizarre orbits, stars that flicker unpredictably, or even free-floating black holes detected by gravitational lensing. Some researchers speculate that the hypothetical planet 9, thought to lurk in our solar system's outer reaches, might not be a planet at all, but a captured primordial black hole, its gravity shepherding distant ice worlds into clustered orbits. Yet for all their destructive potential, these cosmic interlopers might also be creators. A carefully timed encounter could slingshot a frozen dwarf planet into the habitable zone, transforming it into a cradle for life. Or a black hole's gravity might trigger star formation in a stagnant gas cloud, igniting the birth of new solar systems. The universe has a way of turning catastrophe into opportunity, even when the agent of chaos is a speck of infinite density. Detecting these stealthy invaders won't be easy, but astronomers have tricks up their sleeves. Precision measurements of planetary orbits, anomalies in star motions, or even sudden bursts of heat from a gas giant's interior could hint at a black hole's passage. Future missions like the Vera Rubin Observatory with its all-sky surveys might catch the telltale flicker of a microlensing event, a star briefly brightening as a black hole's gravity bends its light. Whether destroyers or architects of cosmic oddities, primordial black holes add a thrilling layer of danger and possibility to the universe's grand choreography. Every solar system, including ours, dances on the edge of chaos, one unseen gravitational nudge away from a new destiny. And that's the most humbling thought of all. The universe doesn't just keep its secrets in the darkness. Sometimes it sends them hurtling straight through our backyard. Neutrinos are cosmic phantoms, particles so elusive they can pass through light years of lead without a single interaction. Trillions stream through your body every second, leaving no trace. Yet these ghostly particles might hold the key to uncovering one of the universe's darkest secrets. When primordial black holes evaporate in their final moments, theory suggests they could unleash a storm of high-energy neutrinos, creating fleeting but detectable bursts that could rewrite what we know about both black holes and particle physics. The process starts with Hawking radiation. As a tiny black hole nears the end of its life, it doesn't just fade quietly, it becomes a frenzied particle accelerator. Quantum effects near the event horizon generate pairs of particles and antiparticles, some escaping as radiation. But near the final evaporation burst, the energy scales reach staggering levels. Protons, electrons, and other particles are torn apart, their components recombining into neutrinos, nature's most aloof particles. For a brief instant, the dying black hole could become the brightest neutrino beacon in the cosmos, flooding space with these ethereal messengers. The Ice Cube Neutrino Observatory in Antarctica has already spotted something peculiar: ultra-high-energy neutrinos with no obvious source. These ghost particles arrive with energies millions of times greater than those produced in supernova or particle colliders, and their origins remain a mystery. Could some of them be the last screams of evaporating primordial black holes? The timing fits. A black hole with an initial mass around 1 billion tons would take roughly the age of the universe to evaporate, meaning countless could be reaching their explosive finales right now, peppering the cosmos with neutrino pulses. Detecting these bursts isn't easy. Neutrinos rarely interact with matter, and their signals are buried in a sea of background noise from other cosmic events. But IceCube's grid of sensors, buried deep in Antarctic ice, is designed to catch the telltale blue flashes of Cherenkov radiation produced when a neutrino finally collides with an atom. If a cluster of high-energy neutrinos appears suddenly from a single point in space, with no accompanying gamma rays or other radiation, it could be the signature of a primordial black hole's death throe. Critics argue that other phenomena, like distant active galaxies or neutron star collisions, could explain these neutrino anomalies, but the energy spectrum holds clues. Primordial black holes would produce neutrinos with a distinct thermal distribution, a smooth curve of energies unlike the jagged spikes expected from astrophysical cataclysms. Future upgrades to IceCube, combined with gravitational wave detectors, might catch both the neutrino burst and the faint spacetime ripples of a black hole's final moments, a 1-2 punch of evidence. The implications go beyond astrophysics. If primordial black holes are neutrino factories, they could help solve lingering mysteries in particle physics, like the exact nature of neutrino mass or whether sterile neutrinos exist. More profoundly, each detected burst would be a direct window into quantum gravity, a regime where Einstein's relativity and quantum mechanics collide. These tiny black holes, smaller than atoms, might be the only places in the universe where such extreme physics plays out in observable ways. For now, the neutrino anomalies remain just that, anomalies. But with every unexplained high-energy event IceCube records, the possibility grows more tantalizing. The universe's smallest black holes could be hiding in the faintest flashes of light under the Antarctic ice, their ghostly echoes carrying secrets from the dawn of time. Black holes have always been the ultimate battleground where gravity and quantum mechanics wage war, and primordial black holes might just be the perfect referees. These tiny cosmic remnants, some no larger than a proton, offer something their stellar-born cousins can't: a front-row seat to quantum gravity in action. As they evaporate through Hawking radiation, their final moments could reveal which of our competing theories, string theory or loop quantum gravity, holds the key to unifying physics. Take string theory's approach. It imagines the universe's fabric woven from vibrating strings, with extra dimensions curled into shapes too small to see. When a primordial black hole evaporates under this framework, its Hawking radiation should carry subtle fingerprints of those hidden dimensions, perhaps particles with unusual energy distributions or unexpected decay patterns. Some models even predict brief, higher-dimensional echoes in the radiation, like ripples from a pebble dropped into a pond we can't perceive. Loop quantum gravity, meanwhile, paints spacetime as a network of interconnected loops. Here, a dying black hole wouldn't vanish completely, but instead rebound at the smallest possible scale, leaving behind a remnant with Planck-scale density. The resulting radiation burst would lack the thermal smoothness Hawking predicted, instead showing jagged spikes or abrupt cutoffs, a quantum scream as spacetime itself resists annihilation. The stakes: imagine catching the evaporation of a primordial black hole with next-generation sensors. String theory's version might shower detectors with high-energy neutrinos in a precise thermal curve, while loop quantum gravity's scenario could produce sudden gamma-ray flashes followed by eerie silence. Even the timing matters. String theory allows for prolonged, flickering deaths, while loop quantum gravity favors explosive finales. Current telescopes aren't sensitive enough to spot these telltale differences, but projects like the Astrophysical Multi-Messenger Observatory Network (AMON) are inching closer. By cross-referencing neutrino, gamma ray, and gravitational wave data, we might soon catch a primordial black hole's last act, and if the data matches one theory's predictions over the other, it would be like finding Rosetta Stone for quantum gravity, a decoder ring for the universe's deepest laws. What makes this so thrilling is the sheer audacity of the experiment. We're talking about testing theories of everything with objects that might not even exist, using the universe's smallest, darkest corners to illuminate its grandest truths. Whether string theory's elegant extra dimensions or loop quantum gravity's knotted spacetime prevails, primordial black holes could hand us the answer written in particles and light. The only thing left is to catch them in the act. Stars powered not by nuclear fusion, but by the slow burn of a primordial black hole at their core. This isn't science fiction. It's a radical reimagining of stellar physics, where the faint glow of Hawking radiation replaces the furious blaze of hydrogen fusing into helium. Picture a star that defies the rules. No need for fuel, no risk of collapse, just an ancient black hole radiating energy like a cosmic battery, sustaining a celestial body for trillions of years. The math behind this idea is staggering. A typical star like our Sun shines because its core crushes atoms together, releasing energy. But replace that core with a primordial black hole, say, one with the mass of a small asteroid, and the equations flip. Hawking radiation would heat the surrounding gas, creating outward pressure to balance the star's own gravity. The black hole's energy output depends on its size. The smaller it is, the hotter it glows. A black hole weighing a quadrillion tons would emit just enough heat to mimic a red dwarf, bathing its outer layers in a warm, steady light. Unlike fusion stars, though, this glow wouldn't flicker or fade. As the black hole evaporates, its radiation intensifies, paradoxically growing brighter as it shrinks toward oblivion. Lifespans enter the realm of the surreal. Fusion stars live for billions of years before exhausting their fuel, but a PBH-powered star could endure for epochs beyond comprehension. The same black hole that takes a trillion years to evaporate in empty space might last only a trillion years inside a star, its energy siphoned off to sustain the stellar structure. That's long enough to outlast every fusion-powered star in the universe, leaving these oddballs as the last beacons in a dark, cooling cosmos. Astronomers call them Hawking stars, and they'd look deceptively normal from afar. Their surfaces might mimic cool M-dwarfs or even Sun-like stars, hiding their exotic engines beneath layers of ordinary hydrogen and helium. But how would they form? One scenario involves a primordial black hole drifting into a molecular cloud, its gravity pulling gas into a dense shell. Over millennia, the gas ignites not from fusion, but from the black hole's radiation, a slow, steady simmer rather than a thermonuclear roar. Alternatively, a PBH could be captured by a dying star, replacing its exhausted core. As fusion sputters out, the black hole takes over, resurrecting the star as something entirely new. Simulations suggest these stars would have unusual internal structures. No turbulent convection zones or differential rotation, just a smooth, radiant gradient from core to surface. The observational clues would be subtle but telling. Hawking stars wouldn't show the chemical fingerprints of fusion, no helium ash building up in their cores, no heavy elements peppering their spectra. Their light curves would lack the flicker of magnetic storms or sunspots, their energy output unnaturally stable. And then there's the telltale gamma-ray signature. Hawking radiation peaks in high-energy photons, so these stars might glow faintly in wavelengths fusion can't produce. Telescopes like JWST could hunt for these anomalies, scanning ancient star clusters for objects that burn too steadily or last too long. critics point out the staggering improbability of a black hole finding and settling into a star's core without disrupting it. But in a universe teeming with primordial black holes, even rare events become inevitable over billions of years. And if just a handful exist, they'd represent an entirely new stellar species, one that challenges our definitions of what a star can be. The most haunting implication: some of these stars might already be hiding in plain sight. The faint, long-lived glow of a black hole-powered star could masquerade as a mundane red dwarf, its true nature revealed only by its refusal to die. In the far future, when all other stars have burned out, these cosmic lanterns might still shine, their dark hearts beating against the infinite night. Black holes are cosmic, one-way streets matter enters, but nothing escapes, or does it? Quantum mechanics has a way of bending even the universe's strictest rules, and primordial black holes might be hiding a secret exit. Some theories suggest these ancient objects could tunnel through spacetime itself, transforming into their hypothetical opposites, white holes, spewing out everything they once swallowed. If true, this bizarre process wouldn't just rewrite the fate of black holes. It could stitch the cosmos into an endless loop of creation and destruction. White holes exist purely in theory, regions where matter and energy burst outward but nothing can enter, like black holes running in reverse. They've never been observed, but the math allows for them, especially when quantum effects enter the picture. For a primordial black hole, the tunneling process begins with Hawking radiation. As the black hole evaporates, shrinking to microscopic scales, quantum fluctuations near its core could become powerful enough to warp spacetime itself. Under the right conditions, these fluctuations might rip open a bridge, a quantum wormhole connecting the dying black hole to a newborn white hole in a distant corner of spacetime. The implications are staggering. Instead of vanishing in a final puff of radiation, the black hole's contents could come roaring back into existence, ejected through the white hole like a cosmic rebirth. Some models suggest this might not even take billions of years. Quantum tunneling could happen in an instant from an outside observer's perspective, making a primordial black hole seem to vanish and reappear elsewhere as a fiery fountain of particles. Now scale this up. Imagine a universe filled with primordial black holes, each one a potential ticking clock waiting to tunnel into a white hole. If enough of them undergo this transformation, their collective outbursts could flood the cosmos with fresh matter and energy, seeding new cycles of expansion. This fits eerily well with cyclic cosmology models, where the universe doesn't end with a big crunch or heat death but resets in an endless loop. Each white hole eruption could spark a new Big Bang, not from a singularity but from the ashes of a previous cycle's black holes. Critics argue this idea stretches quantum mechanics to its breaking point. Tunneling usually applies to particles, not entire spacetime structures, and even if possible, the energy required to sustain such a transition might violate known physics. But supporters counter that primordial black holes, especially microscopic ones, operate at scales where quantum gravity dominates, a regime where our current rules are mere guesses. Future gravitational wave detectors might catch the telltale ripples of a black hole's sudden transformation, or telescopes could spot the impossible. An explosion with no apparent cause, the signature of a white hole bursting into being. The beauty of this theory lies in its audacity. It turns black holes from cosmic dead ends into revolving doors, recycling the universe's material in an infinite dance. Whether proven or not, it forces us to confront a profound question. What if death isn't the end, but just another kind of beginning? And if that's true, the echoes of past universes might be hiding inside the darkest objects we know, waiting for their turn to shine again. Among all the existential threats lurking in the cosmos, few are as chilling or as controversial as vacuum decay. This apocalyptic scenario suggests our universe might be sitting in a fragile, false vacuum state, where a single quantum nudge could trigger a catastrophic phase transition, rewriting the laws of physics in an expanding wave of annihilation. And here's where primordial black holes enter the picture with a terrifying twist. These microscopic relics might be the ultimate cosmic landmines, capable of detonating this doomsday switch under the right conditions. The math behind this idea stretches back to the 1970s, when physicist Sidney Coleman first explored how quantum tunneling could destabilize the vacuum. Under normal circumstances, the probability of such an event is astronomically low, so low that the universe could last trillions of years before it happens randomly. But introduce a microscopic primordial black hole, and the equations shift dramatically. These tiny gravity wells warp spacetime so intensely that they effectively lower the energy barrier needed for vacuum decay, like a boulder rolling downhill instead of climbing a mountain. The black hole's immense curvature acts as a trigger, creating a nucleation point where the false vacuum could collapse into a more stable, but utterly alien state. Assessing the actual risk requires grappling with two uncertainties: the mass distribution of primordial black holes and the true nature of the vacuum itself. If most PBHs are too large, their Hawking radiation would be too feeble to catalyze decay before evaporating. Too small, and they'd have already evaporated without consequence. But those in the sweet spot between 10 to the power of 15 and 10 to the power of 17 grams could linger just long enough to pose a threat while packing enough curvature to tip the scales. The nightmare scenario unfolds something like this. A primordial black hole in this critical mass range drifts into our solar system unnoticed. As it evaporates, its final bursts of Hawking radiation reach energies capable of probing the vacuum's instability. If even one quantum fluctuation within this maelstrom breaches the threshold, it could spawn a bubble of true vacuum expanding at light speed. The boundary of this bubble would be a wall of destruction, rewriting fundamental constants as it passes. Atoms disintegrate, forces unravel, reality as we know it ceases to exist not just here but everywhere the bubble spreads. Critics are quick to point out the speculative leaps in this chain of logic. We don't know if the vacuum is metastable at all. Current particle physics suggests it might be, but only tentatively. Even if it is, the required PBH parameters are razor thin, and their existence remains unproven. Some theorists argue that black holes might actually stabilize the vacuum by acting as cosmic pressure valves, dissipating energy that could otherwise trigger collapse. Yet the stakes compel us to take the possibility seriously. Unlike asteroid impacts or supernova, vacuum decay offers no warning and no survival. It's a total reset button for physics itself. The silver lining: if primordial black holes are abundant enough to pose this risk, their gravitational lensing effects or evaporation signals should eventually reveal themselves. Until then, the universe's ultimate existential gamble remains unresolved, a silent game of quantum Russian roulette where the bullets are smaller than atoms and the prize is reality itself. The holographic principle is one of the most radical ideas in modern physics, suggesting that our three-dimensional reality might be a projection of information stored on a two-dimensional surface, like a cosmic hologram. At first glance, this sounds like pure science fiction, but when you apply it to primordial black holes, the implications become staggeringly profound. These ancient relics could be nature's ultimate storage devices, their event horizons acting as holographic screens that encode information about the universe itself. Think of a black hole's event horizon not as a boundary but as a pixelated canvas. According to the holographic principle, every bit of matter or energy that falls in leaves an imprint on this surface, a kind of quantum tattoo that preserves the information in scrambled form. For a primordial black hole, this becomes even more fascinating. These objects didn't form from collapsing stars. They emerged from the universe's earliest moments, meaning their horizons could carry imprints of that primordial chaos. In essence, each one might be a time capsule, its surface etched with data from the Big Bang's aftermath. This ties directly into the Bekenstein-Hawking entropy formula, which equates a black hole's entropy, a measure of its hidden information, to the area of its event horizon. A primordial black hole, despite its tiny size, would obey this law, packing an astonishing amount of data into a vanishingly small space. To put it in perspective, a PBH the mass of Mount Everest could store more information than all the books ever written, compressed onto a surface smaller than a proton. Where things get truly mind-bending is when you bring in the AD/S/CFT correspondence, a cornerstone of string theory. This proposes a duality between a higher dimensional space, like the interior of a black hole, and a lower dimensional boundary, its horizon. For primordial black holes, this could mean their interiors aren't empty voids but holographic projections. What happens inside them might be entirely encoded on their surfaces. Imagine dropping a book into a PBH. In our world, it's gone forever, but according to AD/S/CFT, every word, every letter might still exist, translated into quantum states on the horizon's flickering surface. Critics argue that testing these ideas borders on the impossible. How do you probe a hologram smaller than an atom, yet subtle clues might exist? If information truly escapes evaporating black holes via Hawking radiation, as some theories suggest, that radiation could carry faint echoes of the scrambled data. Future quantum computers or ultra-sensitive particle detectors might someday decode these signals, uncovering messages from the universe's infancy. The beauty of this theory isn't just its audacity, it's how elegantly it connects quantum mechanics, gravity, and information theory. Primordial black holes might be more than cosmic oddities. They could be the universe's original hard drives, their surfaces storing the blueprints of reality itself. And if we ever learn to read them, we might not just solve the mystery of dark matter or galaxy formation. We might crack the code of existence. Dark energy is the universe's greatest unsolved mystery, an invisible force stretching space-time apart at an ever-increasing rate, yet we have no idea what it actually is. But what if its origins aren't buried in some exotic field or particle, but in the dying breaths of the universe's smallest black holes? Primordial black holes, as they evaporate via Hawking radiation, could be quietly fueling the cosmic acceleration we attribute to dark energy, turning these ancient relics into unseen architects of the universe's fate. The connection hinges on energy conservation at a cosmic scale. When a primordial black hole evaporates, it doesn't just vanish, it transforms its mass entirely into radiation, a burst of energy flooding the universe. Now imagine countless such black holes scattered across galaxies, all steadily dissolving over eons. Their collective energy doesn't disappear, it disperses into the vacuum of space. According to Einstein's general relativity, energy and spacetime are deeply intertwined, meaning this injected radiation could effectively contribute to the cosmological constant, the term physicists use to describe dark energy's repulsive effect. Here's where the math gets fascinating. If primordial black holes were numerous enough in the early universe, their gradual evaporation would release energy at a rate that subtly increases over time, mirroring the observed acceleration of cosmic expansion. Unlike a static cosmological constant, this model suggests dark energy isn't a fixed property of space but a dynamic phenomenon, fed by an invisible drizzle of Hawking radiation. The timing aligns eerily well. Black holes formed in the universe's first second would take billions of years to evaporate, meaning their energy output would ramp up right around the epoch when dark energy's influence became dominant. Critics raise valid hurdles. For this to work, primordial black holes would need a very specific mass range, small enough to evaporate within the current age of the universe, but massive enough to avoid vanishing too soon. Observations of gamma-ray bursts, the expected byproduct of evaporating black holes, haven't yet matched predictions, but supporters counter that the radiation could be spread thin. its energy absorbed by interstellar gas or lost in the cosmic microwave background's noise. The implications are staggering. If verified, this would mean dark energy isn't some fundamental force but an emergent property, a side effect of quantum gravity playing out on cosmological scales. It would also solve a long-standing puzzle: why dark energy's density is so inexplicably small compared to theoretical predictions. The energy injected by evaporating black holes would naturally taper off as fewer remain, avoiding the catastrophic overproduction that plagues other models. Future telescopes could look for indirect clues, like anomalies in the cosmic infrared background or subtle distortions in large-scale structure formation. Even more tantalizing, if we ever detect the faint afterglow of a primordial black hole's final moments, we might catch dark energy in the act of being born, not as a mysterious constant, but as the last whisper of a vanishing cosmos. The universe's greatest expansion may owe its existence to its smallest disappearances. Every evaporating black hole could be a drop in an ocean of dark energy, its ripple pushing galaxies apart one quantum particle at a time. Wormholes, those fantastical cosmic shortcuts bridging distant corners of spacetime, have long been the stuff of science fiction, but hidden within Einstein's equations lies a tantalizing possibility. These tunnels might actually exist if only we could find something powerful enough to hold them open. Enter primordial black holes. These ancient relics might not just be cosmic oddities, they could be the ultimate scaffolding for stable wormholes, turning interstellar daydreams into theoretical reality. The challenge with wormholes has always been their instability. According to general relativity, any tunnel through spacetime would collapse instantly under its own gravity unless propped open by exotic matter with negative energy, a substance that defies everyday physics by exerting anti-gravitational pressure. This is where primordial black holes offer a wild solution. Their extreme gravity, combined with quantum effects near their event horizons, could generate the necessary negative energy densities to counteract collapse. Picture a PBH's intense curvature warping the quantum vacuum around it, creating pockets of negative energy like cosmic counterweights to keep the wormhole's throat from pinching shut. But timing is everything. A wormhole stabilized by a primordial black hole wouldn't last forever. As the black hole evaporates via Hawking radiation, its mass, and thus its gravitational grip, would gradually weaken. Calculations suggest that for a PBH massive enough to anchor a traversable wormhole, the stabilization window might stretch for centuries or even millennia before evaporation takes its toll. That sounds like a long time, but on cosmic scales, it's a fleeting opportunity. Civilizations hoping to harness these tunnels would need to act fast, exploiting the brief equilibrium between the black hole's gravity and the wormhole's tendency to implode. The engineering hurdles are mind-bending. Even if the negative energy requirements are met, traversing such a wormhole would demand precision beyond our current imagination. Misjudge the trajectory, and you might emerge crushed by tidal forces or stranded in an unintended epoch. Some models suggest that quantum fluctuations near the PBH's horizon could introduce chaotic instability, making the wormhole's interior a volatile maze of shifting geometries. Yet the payoff would be unparalleled: a galactic subway system where journeys across light years could become as routine as crossing the street. Critics argue that the required negative energy densities might violate quantum energy conditions, making the entire concept speculative. Others point out that even if wormholes form, they'd likely be microscopic, usable only by particles, not starships. But supporters counter that primordial black holes of certain masses, particularly those in the asteroid mass range, could thread the needle, balancing stability and size. Future experiments with quantum optics or Casimir effect manipulations might reveal whether spacetime can be coaxed into such extreme configurations. The beauty of this theory lies in its duality. Primordial black holes, often seen as agents of destruction, might also be the universe's master architects, stitching space-time itself into bridges between worlds. Whether these tunnels remain mathematical curiosities or blossom into highways for future exploration, they remind us that the cosmos's wildest fantasies might be hiding in plain sight, anchored in the gravity of its oldest, darkest relics. Phantom energy is one of the most unsettling concepts in cosmology, a hypothetical force that doesn't just accelerate the universe's expansion, but does so exponentially, eventually tearing apart galaxies, stars, and even space-time itself in a cataclysm called the Big Rip. Now imagine coupling this apocalyptic scenario with the silent decay of primordial black holes. The result, a cosmic feedback loop where the universe's smallest relics and its most destructive energy fuel each other's worst tendencies, turning the far future into a countdown to absolute dissolution. At first glance, phantom energy and primordial black holes seem unrelated. One is a dark energy variant with repulsive gravity, the other a gravitational singularity. But dig deeper and their interplay becomes eerily symbiotic. Phantom energy's defining trait is its equation of state, a ratio of pressure to energy density so negative, it makes the universe's expansion accelerate faster over time, not slower. As space stretches, phantom energy's density grows, unlike ordinary dark energy's constant value. This runaway effect is what leads to the Big Rip, where even atomic bonds are shredded by expansion. Now introduce evaporating primordial black holes. As they lose mass via Hawking radiation, they inject energy into the cosmos, energy that, according to some models, could amplify phantom energy's grip. Here's how every evaporated black hole converts its mass into radiation, increasing the overall energy density of the universe. In most scenarios, this extra radiation would be negligible. But in a phantom-dominated cosmos where expansion is hypersensitive to energy inputs, even small additions could tip the scales. The radiation from PBHs doesn't just disperse, it becomes phantom energy's accomplice, pushing the universe closer to its rip date. The math reveals a grim dance. Phantom energy's growth shortens the evaporation times of primordial black holes by diluting their surrounding radiation fields, effectively starving them faster. As more PBHs vanish, their energy release further accelerates phantom energy's domination. Simulations of this feedback loop suggest a potential doomsday multiplier effect, cutting the predicted time to the Big Rip by billions of years in extreme cases. The universe wouldn't just end, it would rush toward oblivion on a wave of cascading destruction. Yet there's a counterintuitive twist. Some calculations suggest that in specific mass ranges, primordial black holes could actually stabilize phantom energy's worst excesses. If PBHs are sparse but massive enough, their gravitational pull might locally counteract phantom energy's repulsion, creating temporary pockets of equilibrium. Picture cosmic islands where phantom energy's grasp is weakened, regions where, for a fleeting moment, the rip's tide slows. These islands wouldn't last forever, but they hint at a startling possibility. Even in the face of total annihilation, the universe's oldest objects might carve out brief refuges. The observational stakes are sky-high. If phantom energy is real and primordial black holes exist, future telescopes might spot anomalies in the Hubble flow, patches of space where expansion rates subtly deviate from predictions. Gamma-ray surveys could catch the telltale flashes of evaporating PBHs clustering in regions where phantom energy's effects are mysteriously muted. Even the cosmic microwave background might bear scars of this tug-of-war, its polarization patterns etched with the fingerprints of black holes battling phantom energy's tide. Skeptics rightly point out the uncertainties. Phantom energy remains speculative, its existence inferred only if dark energy's equation of state crosses a theoretical threshold. Likewise, primordial black holes' abundance and distribution are unconfirmed, but the mere possibility of their synergy forces us to confront a profound truth. The universe's end might not be a solitary event, but a chorus of interconnected catastrophes. From the quantum flickers of dying black holes to the vacuum's inexorable stretch, the cosmos's fate could hinge on a partnership between its smallest relics and its most expansive force. Whether this duo accelerates doom or delays it, their potential alliance rewrites the rules of cosmic mortality. The Big Rip was already a terrifying prospect, but knowing that primordial black holes might be silently tightening the noose makes it all the more haunting. The universe's death, it seems, could be a team effort. What if the universe isn't what it seems, not a physical cosmos, but an unfathomably complex simulation running on some cosmic-scale computer? This is the simulation hypothesis, a mind-bending idea that's gained traction among philosophers and physicists alike. And if it's true, primordial black holes might be the glitches in the code, revealing the digital seams of our supposed reality. Think of a video game pushed to its limits. When a system strains to render vast open worlds, imperfections appear, textures pixelate, distant objects pop in abruptly, or shadows flicker at the edges of visibility. These aren't random errors, they're artifacts of computational shortcuts, places where the simulation conserves processing power, now scale that up to the universe. If reality is a simulation running on finite resources, wouldn't it need similar optimizations? Enter primordial black holes. These mysterious objects, with their absurd density and quantum quirks, could be the cosmic equivalent of rendering errors, zones where the simulation's physics engine hits its limits and starts cutting corners. Here's how it might work. In a simulated universe, the laws of physics would be lines of code, and black holes, especially primordial ones, could represent computational overflow. Picture a program trying to calculate infinite density at a singularity. Instead of crashing, the system might approximate by creating a tiny, high-mass object with hard-coded properties, bypassing the need to render the unfathomable physics inside. This would explain why black holes seemingly erase information, violating quantum mechanics. The simulation just stops tracking what falls in, like a game deleting assets that vanish behind a mountain to save memory. The eerie parallels don't stop there. Some theories suggest that if the universe has a minimum scale, a pixel size, like the Planck-length primordial black holes could be manifestations of that limit. Their event horizons might mark the boundaries where the simulation's resolution maxes out, warping space-time into digital noise. Even Hawking radiation fits the metaphor. The random particles emitted during evaporation could be the equivalent of computational rounding errors, tiny discrepancies leaking back into the simulated world. Critics dismiss this as philosophical whimsy, arguing there's no empirical way to test simulation theory. But supporters counter that primordial black holes offer a potential smoking gun. If future observations reveal PBHs with impossible properties, masses, or behaviors that defy standard physics, it might hint at underlying rules written by programmers rather than nature. Even stranger, if these black holes cluster in patterns that resemble optimized data structures like nodes in a cosmic mesh, it could suggest intentional design. Of course, the simulation argument is a hall of mirrors, endlessly recursive. If our universe is a simulation, what's running it? Another universe. And if primordial black holes are glitches, who's debugging them? Yet the possibility lingers, haunting the edges of cosmology. Whether cosmic code or natural phenomena, these ancient objects challenge us to question the very fabric of reality, and wonder if the universe's darkest secrets are hiding in plain sight, waiting for us to read between the pixels. Gravity might not be a fundamental force at all, but a side effect of entropy, the universe's relentless march toward disorder. This radical idea, known as entropic gravity, suggests that what we perceive as the pull of mass is actually spacetime's way of maximizing chaos. And when you apply this framework to primordial black holes, the implications become even more unsettling. These ancient objects could be cosmic entropy engines, their immense gravity not from warped spacetime, but from the way they scramble information at their event horizons. The roots of this theory trace back to physicist Eric Verland's groundbreaking work, which reimagined gravity as an emergent property, a kind of statistical illusion arising from microscopic degrees of freedom we don't yet understand. In this view, a star's gravity isn't because it bends spacetime, but because its presence alters the entropy landscape of the vacuum around it. Now, transpose this idea to primordial black holes. Unlike their stellar-born cousins, PBHs formed in the universe's infancy, where the rules of entropy might have operated differently. Their microscopic event horizons could act as entropy hotspots, pixelated screens where information gets maximally shuffled, creating localized gravitational fields without relying on conventional mass. What sets PBHs apart in this framework is their scale. A black hole the size of a proton with the mass of a mountain would have an event horizon so small quantum effects dominate. Here, entropy isn't just a macroscopic property, it's a frenzied dance of bits flipping at the Planck scale. Some models suggest that in these extreme conditions, the entropic force could deviate from Newton's familiar inverse square law, producing subtle but detectable anomalies. Imagine a primordial black hole drifting through a galaxy. Its gravity wouldn't just bend starlight, it might slightly stick to passing stars, as if spacetime itself were more viscous near its horizon. Critics argue that entropic gravity struggles to explain phenomena like gravitational lensing or the precise orbits of binary pulsars without sneaking traditional geometry back in. But supporters counter that PBHs offer a unique testing ground. If future observations find tiny gravitational aberrations around seemingly empty patches of space, areas where no visible mass exists but where primordial black holes might lurk, it could validate the entropic perspective. Even more tantalizing, if PBHs cluster in ways that don't align with general relativity's predictions but fit entropic models, we might be staring at evidence that gravity itself is a holographic illusion. The stakes go beyond black holes. If entropic gravity holds, it would mean the universe isn't just described by information, it is information, with primordial black holes as its most dense processors. Every tremor of their event horizons could be the universe running its code, one entropy maximizing calculation at a time. Time doesn't flow at the same rate everywhere in the universe. Near massive objects like black holes, it slows to a crawl, a phenomenon called gravitational time dilation. Now imagine that effect concentrated into microscopic pockets, scattered across the cosmos like invisible time-warping mines. Primordial black holes could be doing exactly that, bending time itself on scales so small they'd evade notice until you look closely at the universe's most precise natural clocks. Pulsars, rapidly spinning neutron stars that beam radio waves like cosmic lighthouses, are the perfect tools to hunt for these distortions. Their rotations are mind-bogglingly regular, some ticking with atomic clock precision over decades. But when a pulsar's rhythm stutters, astronomers pay attention. If a primordial black hole passed between Earth and a pulsar, its gravity would subtly stretch spacetime, delaying the arrival of the pulses by microseconds. These anomalies, called timing residuals, might be the only way to spot PBHs too small to lens light visibly. The real intrigue lies in clusters. A swarm of primordial black holes drifting through the galaxy wouldn't just cause one-off delays. They'd create a pattern of erratic timing shifts across multiple pulsars like a symphony gradually falling out of sync. Projects like the International Pulsar Timing Array are already sensitive enough to catch these whispers. In 2016, researchers analyzing data from the Parkes Pulsar Timing Array found tantalizing irregularities in several millisecond pulsars. While most dismissed them as interstellar medium noise or instrumental glitches, a bold few proposed they could be the fingerprints of PBH-induced time warps. Critics argue that other phenomena, gas clouds, asteroid belts, or even unseen planets could mimic these timing quirks, but PBHs would leave a distinctive signature: asymmetric delays. As a black hole moves across the line of sight, Its gravitational field distorts spacetime more sharply on its approaching side than its receding side. This would skew the pulse delays in a way mundane objects can't replicate. Future nanohertz gravitational wave detectors might cross-check these findings, as PBH passages could generate overlapping signals in both timing data and spacetime ripples. The implications stretch beyond detection. If these time dilation bubbles exist, they'd challenge our understanding of quantum gravity. At scales where a black hole's event horizon approaches the Planck length, time itself might become granular, like a digital display flickering between discrete frames. Observing pulsar glitches in concert with Hawking radiation bursts could reveal whether spacetime is smooth or pixelated at these extremes. Even wilder, civilizations advanced enough to map PBH flows might harness them as natural time machines. By orbiting a primordial black hole at just the right distance, you could experience years while millennia pass elsewhere, a real-life twin paradox without the rocket fuel. Until then, pulsars remain our best chance to catch these temporal ghosts, their metronomic beats unraveling the universe's best hidden wrinkles. The multiverse theory paints a picture of reality as an endless froth of bubble universes, each with its own unique physics, inflating eternally into existence. And if this cosmic foam is real, primordial black holes might be the puncture marks, scars left behind when these bubbles collide in the unimaginable vastness of higher dimensional space. Think of eternal inflation like a boiling pot where new universes constantly nucleate as bubbles in spacetime. Most drift apart forever, but occasionally two bubbles touch. When that happens, the collision sends shockwaves rippling through both universes' energy, so concentrated it could trigger the formation of primordial black holes. These wouldn't be the familiar stellar collapses, but cosmic bruises, relics of a multiversal car crash. Some models even suggest these PBHs would carry distinct signatures, unusual spins, mass distributions, or gravitational wave echoes that betray their violent origins. The hunt for these multiversal fingerprints is already underway. If bubble collisions seeded our universe with PBHs, they'd likely cluster in specific patterns like shrapnel embedded in a wall. Astronomers are scanning the cosmic microwave background for peculiar temperature variations, circular scars that could mark where a foreign universe once brushed against ours. Others search for anomalous gravitational wave signals, chirps that don't match standard black hole mergers but instead resemble echoes of a higher dimensional impact. String theory adds another layer. If extra dimensions exist, PBHs formed in a bubble collision might briefly remember their parent universe's physics, subtly altering their evaporation spectra. Imagine detecting Hawking radiation with particle ratios that defy our universe's standard model, a smoking gun for exotic physics from beyond our cosmic horizon. Critics argue that without direct evidence of the multiverse, this remains speculative poetry. But supporters counter that PBHs offer something rare, a potential bridge between untestable theory and observable reality. Whether scars in the CMB or whispers in gravitational waves, these ancient black holes might be the closest we ever get to touching another universe. And if they're out there, they're not just relics of our past, they're messages from realities we'll never see. The universe might be running computations we never even noticed on hardware so alien it defies conventional physics. Picture a primordial black hole in its final moments of evaporation, smaller than an atom yet hotter than a star. As it spews Hawking radiation, particles and antiparticles flicker in and out of existence at its event horizon. But what if this chaotic process isn't just random noise? What if, in some bizarre quantum sense, the black hole is computing? This idea stems from the black hole information paradox, a puzzle over whether information swallowed by a black hole is truly lost or merely scrambled beyond recognition. Some theorists argue that black holes don't destroy information. They process it like a cosmic shredder that leaves behind an indecipherable but recoverable code. For primordial black holes, this processing could happen at scales we've barely begun to imagine. Their microscopic event horizons might act like quantum logic gates, performing operations as particles tunnel in and out of existence. The sheer density of these interactions, trillions per nanosecond, could turn an evaporating PBH into an unintentional supercomputer, crunching quantum data in ways no human-built machine could replicate. Here's the catch: we'd never recognize the output. The computations wouldn't resemble anything like binary code or conventional algorithms. Instead, they'd be buried in the statistical patterns of Hawking radiation, subtle correlations between emitted particles that encode the black hole's solution to whatever quantum state it ingested. It's like trying to read a book by analyzing the ashes of its burned pages. The information is technically there, but reconstructing it would require breakthroughs in physics we haven't even dreamed of yet. The implications ripple outward. If evaporating PBHs are performing quantum computations, they'd be subject to the same limits as any computer, including speed and memory constraints. The Bekenstein bound, a fundamental limit on how much information a black hole can store based on its horizon area, defines its hard drive capacity. A primordial black hole the mass of a skyscraper might hold no more data than a speck of dust, but process it at speeds that dwarf the world's fastest supercomputers. This trade-off, tiny storage but unimaginable processing power, could make PBHs the ultimate quantum accelerators if only we could harness them. Critics counter that calling this computation is a stretch. Without intentional programming or retrievable outputs, it's more like a tree falling in a quantum forest, noise without meaning. Yet supporters point to emergent phenomena in nature, like neural networks in slime molds or fluid dynamics performing optimization problems. If dumb matter can compute under the right conditions, why not a black hole? The distinction between computation and chaos might just be a matter of perspective. Future experiments could look for anomalies in Hawking radiation's statistical noise patterns too structured to be random, hinting at underlying quantum operations. Or we might simulate PBH evaporation in quantum computers, searching for echoes of this unintentional processing. Either way, the idea forces us to confront a profound question. Is computation a human invention or a fundamental property of the universe? The answer might be hiding in the last flickers of the cosmos's oldest black holes, their dying calculations written in particles we're only beginning to understand. From dark matter candidates to cosmic time machines, from galaxy-shaping architects to potential glitches in a simulated universe, primordial black holes have taken us on a journey through the outer limits of physics and imagination. These tiny yet infinitely dense relics of the Big Bang don't just defy our understanding of the cosmos, they shatter it, forcing us to question everything from the nature of gravity to the very fabric of reality. Whether they're lurking unseen in our solar system or evaporating into bursts of Hawking radiation, their existence, or lack thereof, could rewrite the rules we thought were set in stone. Think about it, something smaller than an atom could hold the mass of a mountain, bending space-time like a cosmic funhouse mirror. Or consider the possibility that these ancient objects might not even obey the laws of physics as we know them, perhaps encoding holographic data on their surfaces, tunneling into other dimensions, or even acting as remnants of a previous universe. The sheer range of theories we've explored today, some grounded in meticulous math, others venturing into the realm of speculative fiction, proves just how much we still don't know. But that's the beauty of science, isn't it? Every unanswered question is an invitation to explore further, to push boundaries and imagine the unimaginable. Maybe primordial black holes are the missing link to dark matter. Maybe they're the seeds of supermassive black holes, or the reason our universe is expanding at an accelerating rate. Or maybe, just maybe, there's something even stranger waiting for us to uncover the right clues. So what's your take? Did one of these theories blow your mind more than the others? Are you team PBHs as dark matter, or do you think they might be multiversal scars left behind by colliding bubble universes? Drop your favorite idea in the comments. I'd love to hear which cosmic possibility hooked you the most. And if you're hungry for more mysteries of the universe, don't forget to hit subscribe. After all, space is full of secrets, and we've only just begun to scratch the surface. Until next time, keep looking up and wondering what else might be hiding in the